think we are going live in 3, 2, and 1. So just gonna wait that. Look at this. It takes some time to actually show up on YouTube. There's some delay. Okay, there we are. All right. Okay. I will formally welcome everyone. Thank you for joining us tonight. This is our next talk in the guest speaker series that SJAA does every month. And for those of you who have joined us for the first time, the gist of it is that we used to do these talks in person, of course, and we used to do them around full moon weekend because that's when you don't really have a lot of opportunity to go out and do observing. And we had like star parties on the other nights, which unfortunately we are not able to do right now. But this is one of those programs that we have, which was very easy to move to the digital format. So that's what we have done. And if you want to join us, you can go to sja.net and look at the memberships we have. Or you can also join our meetup. Just search for SJ-Astronomy and you will have all the information. All our events are put on there. All the schedules are up to date. So you can take a look at that and join at least our online events for now while we are still getting out of this pandemic. Tonight, we have a wonderful talk on exoplanets. We have Dr. Jonathan Fortney with us from UC Santa Cruz, and he was actually part of the Kepler mission that happened, I guess, a couple of years ago. I don't exactly know the year now, but he has been studying the physics and chemistry and all the things about these exoplanets. And today we are very delighted to have him with us to hear this talk from him. So, Dr. Fortney, take it away.
Thanks. It's great to be here. Thanks so much for the invitation. I'm always happy to talk about planets. It's really a topic I really enjoy. So, so today my talk is focusing on both discovering new planets around other stars or exoplanets, and also how we can start to characterize their atmospheres with the James Webb Space Telescope, which is launching in about 7 weeks. So let's just jump into it. I should mention I'm a professor at University of California, Santa Cruz in the Department of Astronomy and Astrophysics. And I'm the director of a thing that we call the Other Worlds Laboratory, the OWL. And one of the things we do is we have a big summer program every summer where we invite scientists from all over the world to start to come to Santa Cruz to foster new exoplanet collaborations. So this is one of my favorite images. This is a map of the world, or a map of the quote new world in the year 1550. And so I'll come back to this map again for our very last slide. The thing I like about this map is that just with a little bit of exploring by the year 1550, Europeans could sort of piece together the broad outlines of what was there, right? You can see in North America, you can see Florida, South America, you can see it South America's there. But what folks had in front of them was hundreds of years of exploring to learn what these new lands were like, right? The broad outlines were there, but there was still a huge undertaking to explore and understand what these new places were like. And really, in terms of exoplanets, that's the same phase we are now. We know that these other worlds exist, but we still have a very long time to go in our future to figure out what these other planets are like. And that's the thing that I work on, is trying to understand what planets are like, their temperatures, their atmospheres, their composition. And so what I want to give you a feel for is that today in exoplanets, we're understanding the broad outlines, just like we can understand the broad outlines of these continents, but we're just on the precipice of starting the exploration to figure out what's going on these worlds, just like at this time, people were venturing out into the interiors of these continents to find out what was in store for them. So I think we're all aware that planets certainly come in different sizes, right? So we have Jupiter and Saturn there, Uranus and Neptune, Earth and Venus, and Mars and Mercury. But of course, all these sizes are small. And this is, I think, a nice visualization of the size of the sun compared to the size of Jupiter. In terms of volume, the sun's about 1,000 times larger. And in terms of volume compared to the Earth, it's about 1,000,000 times larger. And this is really the reason why studying exoplanets is so difficult, both because planets are very small compared to their stars, and also because the stars are so much brighter than the planets are. So stars are bright, planets are not. Small planets like the Earth are typically about 1 to 10 billion times dimmer than their parent star. And so the state of the art we have today is not shown on the right, where this young Jupiter-like gas giant planet is about 10,000 times fainter, 100,000 times fainter than its parent star. So about 10 to the 5 times fainter than the parent star. The parent star is blocked out here. But we need to go not to 10 to the 5 times fainter, but 10 to the 10 times fainter, 10 billion times fainter to see potentially Earth-like planets. So taking a picture of a small planet in order to find it requires telescopes that are not yet available. And so on the right, the star's light's blocked out. But astronomers have devised methods that use the star's light to our advantage rather than our disadvantage. And one of those is the transit technique, which I think probably most folks, at least on a call like this, are probably heard of, but I'll spend some time talking about it. So the transit method uses the star's light to our advantage, right? If we stare at some parent star, what we're looking for is the shadow of the planet to pass directly in front of the parent star, block out the parent star's light for a certain amount of time, and then the star returns to its normal brightness. So Jupiter, which has a radius about 1/10 that of the sun, if we could see Jupiter pass in front of the sun, it would block out about 1% of the sun's light. Earth is 10 times smaller, so Earth's shadow is 100 times smaller. So the Earth would block out only about 0.01% of the sun's lights, 1 part in 10,000. So the great thing about the transit method, though, is that you can see these transits happen over and over and over again, and that tells you the orbital period. And so the time for a transit to repeat tells you the orbital period of the planet. And with Kepler's third law, that can allow you to determine the orbital distance. The first planets that were seen to transit are planets, sometimes people call them hot Jupiters. These are gas giant planets on very short period orbits. These are often found in 3 or 4 day orbits. So it's really crazy to think about Jupiter, instead of being in a 12-year orbit, being in a 4-day orbit. Of course, those hot Jupiters are much hotter than Jupiter itself. Some of those are something like 2,000 or even 2,500 degrees. So their atmospheres are very different. So transits have a long history in our solar system. So after Kepler devised his 3 laws of motion in the early 1600s, he was able to predict accurately, for the first time in human history, the location of the planets far into the future. And he predicted when transits of planets should occur. So of course, as seen from Earth, Venus and Mercury are interior to Earth's orbits. And so every once in a while, if the orbits are precisely aligned, we can see Venus or Mercury pass directly in front of the sun. This is a painting, a scan of a painting of Kepler in the upper left. Clearly, today's modern astronomers don't have nearly enough cool facial hair to compete with our brethren from decades past, or centuries past even. This is on the lower left. This is me and my older son, Finn. He's now almost 14, but in 2012, that was a transit of Venus. So Venus transited the sun in 2004 and 2012. If you want to see the next transit of Venus, you definitely have to take your vitamins and eat your Wheaties. That's in the year 2117. I said that right, 2117, the next time we'll see Venus transit from the Earth. But Kepler predicted when the next transit should be, and then he passed away. But in 1639, Crabtree in England became the first person to view a planetary transit, viewing Venus pass in front of the sun. He cast, with a small telescope, he cast that image in his study. This is, of course, a painting with himself, the transit, his loving family by his side. But that really started this science of being able to determine the sizes of planets and use transits to understand planets better. This is one of my favorite astronomical images. This is from the 2004 Venus transit. The Venus transit had already started when the sun was rising off the east coast of Florida. So I really love this image. It's got 3 fishermen, a pelican, and a planet all passing in front of the sun. This is from sunrise in 2004. This image doesn't really have any science value, but I think it's pretty awesome. So I tend to show it every time I give a talk like this. There was a relatively recent Mercury transit. So that happened November 11th, 2019. You can see in the lower left here, of course, Mercury is incredibly small. The next Mercury transit's in 2032. So that's not too far off. Definitely harder to see than the Venus transit, but definitely detectable. So the idea of using transits to study planets goes back centuries. And in 1999, that was the first time a hot Jupiter, a planet around another star, was seen to transit. But already before that, in the 80s, Bill Barucki, who was a scientist at NASA Ames, which is, of course, in Mountain View in Silicon Valley, had the idea that if you could build a specially designed space telescope, this would be a way to potentially find other Earth-sized planets and orbiting other stars in the Milky Way galaxy. They submitted a potential NASA Discovery mission proposal to make the Kepler mission, and it was turned down 4 times. Finally, on the 5th time, they had figured out exactly how to make such a mission happen, and NASA approved that mission. So the basic idea is if you sample a large enough number of stars, you can determine the fraction of sun-like stars that have Earth-sized planets in Earth-sized orbits. So of course, we know what Earth size is. That's around the same size as Earth, right? Planets, our orbit is a very nice temperate orbit, not too hot, not too cold. We'll come back to that in a little while. That's sort of Goldilocks zone. So the idea of the Kepler mission is it's really important to have a large sample size, right? If you sample 10 stars and you don't find any planets, does that mean that planets are rare? Well, you don't know. You only sampled 10 stars. So the idea of the Kepler mission was to sample about 100,000 stars. Such that if you didn't find any Earth-sized planets with 100,000 stars, then you know such planets are inherently incredibly rare. And that was the idea behind the Kepler mission. It was really a statistical mission to tell us how common different sizes of planets were. And this was the Kepler field chosen just out of the plane of the Milky Way. The Milky Way plane is too dense with stars. You want to be a little bit out of the plane. And it was just in the constellation Cygnus there. So Kepler was a 100 megapixel space camera built to do one thing exceptionally well. In a lot of ways, it wasn't nearly as powerful as like the Hubble Space Telescope, but Hubble doesn't have the ability to monitor stars for many years at a time, where the Kepler mission was built to do this one thing incredibly well. So the important planets for the Kepler mission were those in this area that we call the habitable zone. The habitable zone is an area of planetary temperatures where liquid water can potentially exist on the planet's surface. So in a diagram like this, along this axis, this is how bright your parent star is compared to the sun. This is half the sun's luminosity, a red dwarf star. This is twice the sun's mass, twice the mass of the sun, bigger, brighter, half the mass of the sun, smaller, redder. And so in our planetary system, Earth is inside this, is in this band in the habitable zone. Venus is too close. Mars is just a little bit too far. If Mars had a much, much thicker atmosphere, it probably would be okay. So if you're around a smaller, fainter star, this habitable zone is closer in. If you're around a bigger, brighter star, this habitable zone is further away. So the idea of the Kepler mission was to find Earth-sized planets and potentially as many as possible in this habitable zone. Now, the hard part, of course, is that Earth, of course, is in a one-year orbit. And so it's quite difficult to stare at stars for multiple years to see these tiny dimming events. So the Kepler mission was optimized then for finding potentially habitable planets, let's say those around the size of Earth, 3/4 to 1.5 times Earth's radius, in this habitable zone, orbits of around 1 AU. The AU is the distance we orbit at. And so it continuously monitored 150,000 stars for 4 years, and it was a 1-meter space telescope. There's a human there for scale. There's the 1-meter diameter of the mirror, basically, and there's solar panels, of course. So the idea was to stare at one patch of sky without blinking, basically, for about 4 years to be able to see these tiny dimming events, to look for these transiting planets. And so to think about how tiny these dimming events are, we can look at the Transamerica Pyramid. Now, if you imagine the Transamerica Pyramid all lit up, okay, let's say we can see all those lit up windows. Let's imagine that's how bright the parent star is. And so what the Kepler mission was looking for was, if you imagine someone pulling down a shade about 1 foot in one of the windows, in all the windows of the Transamerica Pyramid, and that dimming lasts a few tens of hours, and then it goes back up again. And then then you have this constant brightness for another year, and then a year later, someone pulls the shade down by 1 foot for maybe 20 hours and then puts the shade back up. What we're looking for is this 1 part in 10,000 dimming event, right? An Earth-sized planet only blocks out 1 part in 10 to the 4 of the parent star's light. And it happens for several hours, and it only repeats once per year. So it's an extremely technically challenging thing to build a space telescope that can see such a tiny dimming event. And so what Kepler data kind of looks like is this sort of thing here. This is, let's look at the bottom. This is the flux from the parent star. And so 1.000 is the normalized flux. That's how bright the star is normally. So every once in a while, there's like data gaps here, but this is over the course of about 500 days. And what you can see is this sort of fuzz, right? This fuzz below the main band of light. And this fuzz is when planets pass directly in front of the star, blocking out some of the star's light. Kepler 11 was the 11th planetary system found by the Kepler mission, and it was extremely unusual. Or in some ways, we now know it's not quite as unusual as we thought it was. But this system has six transiting planets, all bigger than the Earth. This is one of the exotic planetary systems that the Kepler mission found. So these little yellow balls, this yellow ball is every 11 days. So there's one here, one there, one there. This planet's in an 11-day orbits. Every time it passes in front of the star, it blocks out some of the star's lights, and the star gets a little bit dimmer. So you can see this is tiny dimming events right here. This is a 0.1% dimming down to there. This red ball is a planet that transits every 13 days or so. And so at the time, this Kepler 11 system was extremely interesting. It made the cover of the journal Nature, 6 New Worlds. The thing that's amazing about this system is that it's the most densely packed planetary system yet found. 5 planets, all larger than the Earth, all orbit within Mercury's orbit around the sun. So, of course, inside of Mercury's orbit in our planetary system, there's really essentially nothing. I think there's been 1 asteroid found, but it's basically empty. But in this planetary system inside of Mercury's orbit, there's 5 planets, all larger than the Earth. And perhaps most interestingly, the parent star looks almost exactly like the sun. It's what people call a solar twin. But yet the planetary system that it formed, it seems nothing like our own planetary system. And we really don't know why that is. If someone asked me that question at the end, I don't know. Nobody knows yet. It's just part of the variety that we're seeing. So this system was found in the year 2011, and that was really in the heyday of the Kepler mission. The mission launched in 2009, and that was around the time that I joined. And then the main mission lasted from 2009 to 2013. And then it had an extended mission until about 2018, I think, where it was staring at different patches of the sky, finding additional planets. So I have a little movie here of what the Kepler 11 system might look like. You can see the star is dimming every once in a while. And so it has 6 planets, 5 closely packed, and then a 6th one a little bit further away. And if we make them give trails, you can kind of see them going around. So the innermost planet's in an 11-day orbit. The furthest out planet is in, I forget, I think it's around a 100-day orbit. But it's a system really unlike our own in that all the planets are bigger than the Earth and they're all much closer in than we find in our own planetary system. So it's going to start. We'll come back. Let's start back again. All right. So this is a little movie that shows how important the Kepler mission was in terms of finding new planets. So this is the size of planets relative to Earth. So Earth is, of course, 1. Neptune's about 4 times Earth's radius. Jupiter's about 11 times bigger. And so this movie starts in 1989. You can see in the lower right. That was when the first sort of, massive, potentially planet-like object was found. And a lot of these, it's color-coded. So the blue objects were found with this radial velocity Doppler wobble method that you might have heard of. And then the transiting planets are mostly going to be in pink. So we'll start to run that from 1989, 1995, 96, 97. So we'll let it go for a little while. So when I was in grad school in 1999, starting out, this is the way things looked like when I was a young scientist. And so we'll let the movie go till about 2009 here. And so at that time, around the time of the Kepler launch, you could see we'd found, I don't know, maybe around 200 planets or so. The transiting planets that pass directly in front of the parent star that we can see, the ones that were found at the time were mostly these big gas giants like Jupiter. The planets that we could see from this radial velocity wobble method of the parent star's Doppler shifted light, that was also finding mostly Jupiters. So what we knew at the time was that gas giants like Jupiter were relatively common, but we really had no idea how common these smaller planets were at the time. So we'll zip ahead a little bit. We'll start in 2009. This is when the Kepler mission launched. And we'll look at planets. Oh, it's going to repeat. Okay, that's fine. It's a nice movie. 2006, 2008, 2009. Okay, so then we'll go past 2009. Okay. 2010, 2011, 2012, 2013. Okay, so you can see that other methods were finding more planets, but you can see basically that other methods were mostly finding gas giants. These relatively smaller planets are much harder to find. So the question really was, how common are various sizes of planets? And in 2013, the Kepler data release, the first Kepler data release, really answered this question. What Kepler showed us is that although gas giant big planets like Jupiter are relatively common, they pale in comparison to how common smaller planets are. You can really see easily with your own eye as you go from 10 radii times out of the Earth to 4 to 1. Once you get below the size of Neptune, the frequency of planets goes up dramatically. So planets smaller than Neptune are much, much more common than planets larger than Neptune. And so this is where the Earth would sit in about a 300-day orbit. Of course, the transit method is biased towards finding close-in planets. So planets out here at these longer periods very likely do exist. We have no reason to think that they don't, but they're much harder to find. So this region is what you would call incomplete. But Kepler found around 5,000 planets, which really changed our idea of how common planets are. Planets are common, and planets relatively similar in size to the Earth are incredibly common. So I mentioned this before, that whether or not your planet is potentially in the habitable zone or not depends on how bright your parent star is, right? In a diagram like this, green is kind of our Goldilocks zone, not too hot, not too cold, right? And that's where the Earth sits today. This red region is too hot, this blue region is too cold. Around a hotter star, this habitable zone is further out. Around a dimmer, fainter, redder star, this habitable zone is closer in, right? If your campfire is very small and faint, you want to be packed in really close to the campfire to stay warm, right? And so this is the same thing is true for potentially habitable planets. And so stellar stars are classified by this old classification system where the sun is a G-type star. The biggest, most massive stars are O stars. The smallest, fainter stars are M stars. And generations of young astronomers know this by "Oh, be a fine girl, kiss me," or "Oh, be a fine guy, kiss me." That's the mnemonic for remembering this strange classification system. But the sun is a G-type star, and so you often hear that the sun is kind of an average star. It's average. You hear that a lot, and like that's kind of true, but it's mostly not true. I don't want to say it's wrong, but it's pretty close to being wrong. So these O and B type stars are really massive, very bright, but they're inherently extremely rare. These small M type stars are inherently incredibly common. So we look at a diagram like this. So these are all stars within 30 light years of the sun. There's about a little more than 300 stars within 30 light years of the sun. There's no O stars, no B stars, only a few A and F stars. These are sun-like stars, these yellow ones, the G types. But these small, faint M stars, there's 246 of them within 30 light years. So something like 75% of all stars in the sky, 75% of all stars in the Milky Way are these small, faint M stars, these guys way over here down on the left, okay? So is the sun an average star? Well, not really. I mean, it's kind of in the middle. There's some a lot bigger and more massive, and there's some a lot smaller and fainter. But if you think about the average, the most common, these are really the M stars. I think maybe a lot of amateur astronomers know this, but you know, these 246 M stars that are in the sky, guess how many of them you could see with your own eye, unaided eye? Zero. They're small and faint, and they put out almost all their energy in the infrared. They put out very little visible light. So it's crazy to think that if we had infrared eyes, we would walk out and see a sky that looked totally different than the sky that we see. So M stars, they're everywhere. So M stars are a small campfire, but they dominate in number. And one of the probably the most interesting planetary system we've found around an M star is called TRAPPIST-1. If you Google that, you'll find tons of stuff about it. But the amazing thing about TRAPPIST-1 is that its parent star is 1,000 times fainter than our sun. It's really small, really faint. So to scale, this is our planetary system with Earth in the habitable zone in this green region here. The TRAPPIST-1 planetary system, which has 7 planets, is to scale down here where my arrow is, really tiny. So if you zoom in, there's a faint star, not shown to scale. But there's TRAPPIST-1, B, C, D, E, F, G, and H. And planets E, F, and G look like they're all in this star's habitable zone. So the amazing thing about the TRAPPIST-1 system is that we see 7 different planets transit past directly in front of their parent star, and 3 of them look like they're potentially in the star's habitable zone. So it'd be interesting to know more about them. So we're about 8:30, so I'm making good time. I think we're in good shape. So with all the Kepler data now analyzed, because the data's been done for several years now, one of the amazing things that we've learned that we did not know a decade ago is that about 25% of sun-like stars have an Earth-sized planet in the habitable zone. And this is really going to be the answer. Better Kepler data analysis techniques might change this answer a little bit, but within about a factor of 50%, this number is about right, about 25%. So about a quarter of sun-like stars in our galaxy have an Earth-sized planet in this Goldilocks zone, in the habitable zone. But the amazing thing is that this number is far higher for these faint M stars. About 50%, about half of them, have an Earth-sized planet in the habitable zone. I mentioned M stars are 75% of all stars. There's about 100 billion stars in the Milky Way. That means 75 billion M stars. And that means 35 billion plus potentially habitable planets in our galaxy. Do we know these are actually inhabited? We certainly don't know that yet. But in terms of Earth-sized planets in the habitable zone in our galaxy, the Milky Way, this number is something like 35 billion. So that's a lot of systems to check out over the course of some lifetimes. So the first way we're going to try to really interrogate the atmospheres of these other planets to figure out more about them is with the James Webb Space Telescope. This is a NASA flagship class telescope that was first envisioned about 30 years ago. When I was a younger astronomer, the launch date for this was supposed to be 2013. Here we are 8 years later, but I'm still just as excited as I was then. And so the idea behind the James Webb Space Telescope is that it is able to do a number of things. It was originally designed back when it was envisioned to look at the first galaxies forming in our universe. But one of the nice things about James Webb being delayed is that they were able to modify a number of the instruments to also be able to take spectra of planets around other stars or exoplanets. And so the main mirror of James Webb is 6.5 meters across. So in terms of collecting area, it's about 7 times larger than Hubble. And it's really going to be revolutionary in terms of lots of different areas of astronomy, but perhaps most important, or well, most important to me anyway, is planets. I'm sure it'll do great things for galaxies too. So the thing it's going to try to find is this very faint atmosphere. So this is an image of Venus passing in front of the sun from 2012. And so what you see in this image of Venus is this faint ring over here. Now, why would Venus have this faint ring around it? It has that faint ring because Venus has an atmosphere, right? And so this is light from the sun scattering through the clouds, maybe refracting a bit in Venus's atmosphere. And amazingly, Lomonosov, a Russian astronomer in the 1700s, with his small, feeble 1700s era telescope, was able to see this faint ring around Venus during a Venus transit in the 1700s. He actually discovered that Venus has an atmosphere. It's the same basic idea that we want to use the James Webb Space Telescope for. We want to see these planets pass directly in front of their parent star. We want to look for extra absorption due to molecules in the planet's atmosphere that absorb an extra amount of that parent star's light. And so the way I want to think about this is, if Venus didn't have an atmosphere, we wouldn't see this ring around it, right? If Venus has a really puffy, thick atmosphere, this ring would be taller and bigger. If Venus had a really thin atmosphere, that ring would be smaller. And what we want to look for is absorption features due to that ring, right? So water vapor, methane, carbon dioxide, these molecules absorb light differently. And so this is sort of a cartoon of different wavelengths. This is the infrared. So this is 1 micron out to 30 microns. And it's color coded by different absorption features. So water vapor absorbs at around 1.4 microns, 2, 6, 25 to 30 microns. Carbon dioxide famously absorbs strongly at about 15 microns, and over here at about 4.5. Methane's a strong absorber at 8 microns, 3 microns, 2. Other gases like ozone, CO, nitrous oxide, all these different molecules have different chemical fingerprints. And so what we want to use the James Webb Space Telescope for is to look for these extra absorption features that we hope to see in the atmosphere of an exoplanet. And this is one of the things I work on a lot in my research group, is making computer models of the atmospheres of other planets around other stars and comparing them to data that we get from observers or data that we hope to get soon. This is a simulation of what we might be able to look for TRAPPIST-1e. So TRAPPIST-1e is this guy here at the inner edge of the habitable zone around this faint star. These are different possible atmospheres, like a steam atmosphere, a cloudy steam atmosphere, a carbon dioxide dominated atmosphere, or an atmosphere similar to Venus. This would be if you're able to add up 50 transits together or 30 transits together. What we'd like to see are things like water vapor absorption, carbon dioxide absorption. And you can see these are very small signals. And this is the simulated noise on the spectrum that you might get from the James Webb NIRSpec instrument, which can look from about 1 to 5 microns simultaneously. So in my group, these are the sorts of things we do. We make computer models to try to understand what the composition of exoplanet atmospheres are. And so what you need to be able to detect the atmospheres of these planets is find good targets. So TESS is already the TESS, TESS is the Transiting Exoplanet Survey Satellite. That's another space mission that's flying today. So Kepler stars were typically very faint. Kepler stared in one patch of the sky for 4 years and found planets around very faint parent stars. The thing about a faint parent star is that following up with the James Webb Space Telescope is very challenging. What you want to have is a nearby bright parent star. And that's where TESS comes in. So TESS is only searching around bright stars all over the sky. And so what TESS does is it maps the sky. It has 4 cameras. And over the course of about a year, it maps the celestial southern hemisphere. And then over the next year, it maps the celestial northern hemisphere. And TESS has already been doing this for several years. It's currently in its extended mission, where it's mapping the sky a second time. And so over the course of its lifetime, TESS will find probably even more planets than Kepler found all over the sky. In red here, these regions are shown in red because these are regions where TESS has incredibly good coverage, right? Where these 4 cameras essentially overlap, and it can find longer period planets there. And these kind of celestial north and south pole areas are also quite good for James Webb to do long observations in those areas as well. So TESS is still flying right now. It's finding a large number of planets around nearby bright stars, such that we can use the James Webb Space Telescope to follow them up. So the James Webb launch, as I mentioned, is scheduled for December 18th, 2021. It's actually launching not from Cape Canaveral, Florida. It's launching from French Guiana on the northern coast of South America. You might say, why in the world is it launching from there? That's because James Webb is a joint NASA, ESA, and Canadian project with most of the money from NASA. But ESA is providing the launch. It's going to launch on an Ariane 5 rocket. And so the James Webb Space Telescope was assembled at different NASA research centers in North America. Goddard out in DC. There was lots of tests done at Johnson in Houston. And then the final work was done at Northrop Grumman in Los Angeles. So it was put on a boat in the LA harbor, and then it went down along the Pacific coast. Then it had to cross the Panama Canal. And then after crossing the Panama Canal, it had to make its way over to French Guiana, because that's where all the ESA launches are. There was a definite worry about pirates maybe trying to hijack the boat, because the cargo is worth about $10 billion. So that's hard to, that's a lot of bang for your buck if you're going to hijack a boat. But so the day it was launched from the Los Angeles harbor was kept secret, so that the world didn't actually know when it left. But it made its way to French Guiana about a week ago. So I don't know exactly which canister it is. I think it's maybe this one, but it arrived in French Guiana about a week ago, and it's off the boats, and they're going to be doing a few final tests, and then it's going to be put up in this Ariane 5 rockets. I mentioned before very briefly that it has this big mirror, and in reality, the mirror is made out of these hexagonal segments. So these hexagonal segments actually, it has to fold up, otherwise it won't fit in the rocket. So it actually folds up into 3 parts, and then after it launches, it has to actually unfold. Of course, we all hope that works out just right. Okay, French Guiana, yes. So I just want to mention that we have a lot of James Webb Space Telescope involvement at UC Santa Cruz, involving myself in the lower right, but also a number of other scientists. My colleague Ruth Marie Clay studies how atmospheres are lost, how they evaporate over time and are lost to space. My colleague Shi is in the Department of Earth and Planetary Sciences. He studies atmospheric chemistry. And then my colleagues Natalie and Andy are actually 2 of the leaders of some of the first James Webb Space Telescope data that's going to be coming down. There's about 10 programs that get a first view of James Webb Space Telescope data. There's 10 programs that cover galaxies, stars, and there's 2 of them that study exoplanets. And it so happens that Natalie is a leader of one of these programs and Andy Skemmer is a leader of another program. So we really have a lot going on in terms of James Webb Space Telescope observations of exoplanet atmospheres here in Santa Cruz within the Other Worlds Laboratory. So probably in June or July, that's when we'll see the first data coming down to tell us about other planets, their atmospheres. So I'm getting close to the end. It's maybe 5 or 10 more minutes at the most, probably closer to 5. So what I find really exciting is that we're really at the precipice now to understand the atmospheres of planets and systems that look nothing like our own. But of course, one of the things you might be wondering is what about systems that do look like our own, right? So the planets we're going to mostly be studying with the James Webb Space Telescope are those very close to their parent star. A lot of them are going to be around stars much smaller and fainter than the sun. We'll be studying some potentially small planets in the TRAPPIST system, but we'll also be looking at a lot of hot Jupiters as well. So a lot of these planets may not have a lot of similarities with planets in our own solar system. A lot of them will be much hotter. And so what we'd like to be able to do is look at systems like this. This is, of course, this is our system. This is a computer simulation of what an advanced space telescope might be able to see in our planetary system. So this is a synthetic image of what an alien space telescope looking at our planetary system might be able to see. So we have the sun blocked out, we have Venus, we have a very faint Earth, 10 billion times fainter than the parent star. We have Jupiter, only about 1 billion times fainter than the parent star. It's further from the sun, but it's a much bigger sort of reflector. And the question is, can we build a space telescope that might be able to take images like this of other planetary systems to better understand planets that maybe are better, that are more like our own? And so this is something that might happen in a few decades' time. So there's an organization meeting right now that I'm a part of called Astro 2020. It's a decadal survey. So once per decade, a collection of United States astronomers makes a path for what United States astronomy should do in the coming decade and the decade after that. And so one of the topics that we've talked about for the past year is the need for a new NASA flagship space telescope. Beyond the James Webb Space Telescope that's launching in 6 weeks, and then beyond the Roman Space Telescope, which is launching later in the 2020s. And there's 4 different contenders. One is called LYNX. It's a very advanced X-ray telescope that would replace the current Chandra telescope that's still operating in Earth orbit. One is called Origins. Origins is kind of like an extremely advanced James Webb successor that would work in the mid-infrared. And 2 of them are more focused on exoplanets. So one is called HabEx, the Habitable Exoplanet Observatory. And one is, as a funny acronym, people pronounce this LUVOIR, even though it's not really French. It's the Large ultraviolet optical infrared telescope. This would be kind of like, a super version of Hubble. And so Lynx and Origins would not be able to look at Earth solar systems that are like our own, but HabEx and LUVOIR would. So LUVOIR would be very large. It would be some sort of James Webb or bigger, and it would be able to block out the parent star's lights inside the telescope to see these faint planets. HabEx would have a different design where it would actually fly a separate spacecraft that would fold out like a sunflower. And this sort of sunflower thing would block the parent star to be able to see the faint planet. And so in the next few weeks, this organization, Astro 2020, will be releasing their recommendations for what NASA and the National Science Foundation should do in the 2030s and the 2040s to push astronomy forward. So one or more, perhaps, of these missions might end up being selected. So in my last few minutes, I want to bring up my concluding thoughts. So exoplanets get talked a lot about in astronomy. There's lots of exoplanet articles in the popular media, but we're really only just beginning to understand how planetary systems are built. There's really solid evidence for tens of billions of planets in the habitable zone in our galaxy. I mentioned this number of about 35 billion. Our planetary system is perhaps a bit rare in that it's not the typical layout. However, in some ways, it may be kind of common in that we do know that Earth-sized planets in the habitable zone are common. So the next stage is to characterize the planets themselves and find out more about what their atmospheres are like. This is the kind of work we specialize in my group in Santa Cruz. This really will take some patience, but it's really the next era of exoplanets, and it's really nearly at hand. And so what I hoped I conveyed to you today is that although we've found over 5,000 exoplanets already, and we know a lot about exoplanet orbits, we still don't really know yet a lot of what these planets are like. Just like in the year 1550, these continents had been found. Of course, they were always there, but they'd been found. And there were still hundreds of years of exploring in front of us to determine what these new lands were like. And that's really at the realm we're at in exoplanet science, where we know these planets are there. We've found thousands of them, but now we're just starting the exploration to tell us more about what these new worlds are like. So that's the end of my talk. I'm happy to take any questions.
Thank you so much. That was wonderful. And just a side note before we get into Q&A, if any of you have National Geographic magazine subscription, they did an issue on James Webb Telescope recently. So you might want to check that out. It was pretty cool. With that, Q&A, it's an open forum. If you want to put your question in chat, I just see Stefan already did that. I can pass it on or read it aloud, or you can unmute yourself and ask your question yourself. But since Stefano has already put one question here, I'm going to start with that. Thank you, Professor, for this really fascinating presentation. I would like to ask, how do you distinguish a transit of a planet in front of a star from a Cepheid star or from a periodic sunspot on that star?
Yeah, that's a great question.
Mm-hmm.
Cepheids are those are easier to that's not really a problem. So the thing about a transit is that the star looks boring and constant, and then you block out a small amount of that star's light, and then it goes back. A Cepheid tends to be variable, more like a sinusoid, up and down, more or less. A sunspot can be a little bit harder, a little bit. So if you imagine a star that only has one sunspot, right? So when that sunspot is on the backside of the star would appear relatively constant. And then when that sunspot came into view, you would see a dimming that lasted half of the star's rotation period, and then it would disappear again. One of the things that helps is that the sun rotates every 27 days, something like that. It's about 27 days, as I recall. So, and so that dimming would last sort of 27 days. And so a lot of the time, the transit dimmings that we see are typically much shorter, right? So a lot of the transits we see are typically 3 to 10 hours. And so that dimming time is much shorter than a typical sort of sunspot crossing time. So the time scale is different, which helps us out. That's probably the best answer to the question, is the time scale can be a lot different.
Thank you for that. Any other questions? I'm also looking at the YouTube channel or YouTube talk to see if anyone posting questions there, but I don't see any there yet. So anyone in this forum?
Professor, my name is Viplav.
Hi.
Very fascinating talk.
Thanks.
Can you hear me?
Yes, I can.
Okay. I had a kind of very basic question here. That it just amazes me that something that small, a dot, in front of a bright star, and the lights are coming out from there. Is there no diffraction, refraction kind of things happening, which kind of makes the planet invisible in front of such a big? When does that happen, these kind of problems?
Yeah, that's a great question. So people have spent a lot of time modeling that based on what we know about how atmospheric refraction. And it ends up being a relatively minor effect. And the reason why is that because these planets are relatively close to their star, you would need that refraction to be relatively big. If you imagine the planet being extremely far from the star, let's say, I don't know, a light year away, really far away, then a tiny bending of light, a tiny change in that angle would be important. But because the planets are so close, you need an incredibly big angle change. And it's just that atmospheres are not refractive enough to cause that large of an angle change. On the opposite, in our solar system, we can see these things called occultations, where if we look at Jupiter, sometimes we can see bright stars pass behind Jupiter. And in that case, that star is incredibly much further away than Jupiter is. And if we look at solar system occultations, there we see a lot of refraction. There we can see our solar system's planets' atmospheres refract the light of distant stars. And it actually tells us about the density of their atmosphere from the fact that they're able to refract that light. So it's a great question. And it's something that people were incredibly worried about at first, to be honest. And only with better observations and better models did we realize that it does happen, but it's a pretty minor effect.
Thank you.
Sure.
Let's see. So I have a couple of questions in chat. Joey is asking, has a specific first light target has been identified for the James Webb Space Telescope?
I'm sure there is. I actually don't know what it is. My guess is that the first light for James Webb will be like a beautiful giant galaxy. Mm-hmm. And that'll be sort of the first image that we see. That'll probably be, I don't know. I would guess maybe February or March. I'm just, mm-hmm. I don't really know, but I know that the main science operations, if everything works correctly, are supposed to be sort of May and June. Mm-hmm. So I would guess, big galaxy that they could put on the front page of the newspaper probably is the sort of thing they'll do first.
Oh, I see. I mean, whatever gets public's attention, right? Like, because these kind of missions could use like public support in general for advancement of science. Marianne has a question about hot Jupiters. With hot Jupiters, do they tend to bulge the star? Do you see this actually?
Yeah, so I think the question is does the gravity of the planet raise tides on the star like a tidal bulge? Yes, the bigger effect is actually tides raised on the planet by the star that makes the planets actually bulge, and that makes these hot Jupiters actually somewhat football shaped, like they're prolate. That's like a football shape, and they bulge towards the star and also away from the star. So there's certainly should be a tidal bulge on the star, but the effect is kind of too small for us to see. But that reverse tidal bulge actually can be big enough for us to see, and that it actually changes the shape of the planet compared to a sphere.
So I'm sure you get this question a lot. I'm just going to ask my question while I wait for more questions to come in. So there are a lot of habitable planets that we know are out there. What do you think how much is really a chance of finding intelligent life on these planets?
Yeah, so with James Webb, right? So we're hoping in these small planets over the course of many years to build up enough signal to be able to see things like methane, carbon dioxide, maybe ozone. So we would be able to see things that are, at least on Earth, byproducts of life. But of course, that doesn't tell us at what stage that life would be, right? So I don't, yeah. So in terms of intelligent life, right? It's intelligent life there. It's hard to say, right? So, I mean, there you'd want to do different searches, right? So that's, historically that's called SETI, the search for extraterrestrial intelligence, but they're sort of rebranding now. And now people call that searching for technosignatures.
Oh, I did not know about this.
Instead of searching for biosignatures, which would be signs of life, they search for technosignatures, which would be signs of technology.
So SETI is now SET-S, like they changed the name?
I would say people who work in SETI, they would now say they are looking for technosignatures. And they do not use the word SETI nearly as much as they used to.
Interesting.
But it's some of the same techniques. It's looking for radio waves. It's also looking for laser pulses in the optical. That's another relatively newer thing. People have also thought about if a very advanced civilization might advertise their existence by building planet-sized structures of very odd shapes and have them transit in front of their parent star. So, like, what does the transit of a giant triangle the size of the Earth look like compared to a sphere?
Right. I mean, I'll admit my question came a little bit out of the fact that I recently read Three Body Problems. So I think my brain is slightly on that track.
No, it's certainly on everybody's mind. It's difficult, right? It's very difficult.
It's very difficult. I agree. Well, we have one more question here. There is probably a huge demand for JWST observation time. How much time do you get?
Yeah, so that's a great question. So the way the Hubble Space Telescope and James Webb work and other space telescopes is that there's a time allocation committee, a TAC. And so I've served on, not the James Webb TAC, but I've served on other TACs. And so basically you write proposals about what targets you want to look at and why, how much telescope time you need, why it's interesting. And then there's different panels. So there's like an exoplanet panel, there's a stars panel, there's a galaxy panel, a cosmology panel. And so these panels, they look at the stuff that and the panels are made up of just, astronomers from around the country, around the world. And they sort of rank their proposals. and they rank them from what seems the most exciting or to the least exciting.
Mm-hmm.
And then at the end, the panel might end up with 500 hours of observation time. And then you go down from the top to the bottom, and okay, that gets us to proposal number 7. And then 8 and below, better luck next year. And so
interesting.
A telescope like this is always what people call oversubscribed. There's more time people are asking than is available.
I bet.
And so I think this year it was about 5 times oversubscribed. So about 20% of the proposals got time and 80% didn't. Wow.
Okay. Well, yeah, we will look forward to the launch anyway, because it's been long due. Paul has a question about the M-stars. With M-stars activity, there is a concern about the solar flares may have a more extreme effect on the habitability of planet. Well,
yeah,
it's not really
so
a question, it's a statement, really.
Yeah. Oh, that's true. Yeah. Well, these faint M stars, right? They're faint. They have a small campfire, right? So the planets want to be close in to stay warm. But it turns out that these faint M stars are actually, although generally they're faint, when they're young, they're actually quite brighter than you would think they are. And they also pump out a fair amount of flares and ultraviolet light over time. And so some people have definitely suggested that they may not be great places to look for life, but we don't know if that's true or not. That's why we have to explore and find out.
Yep, that's true. Let's see, any other last minute questions? I'm not finding any. The YouTube channel is very quiet, but we have quite a few people here. So if you have another, want to squeeze in another question, give it a couple of minutes. Okay, quiet crew. All right. Well, thank you so much for joining us today. And that was a lovely talk, yet another great talk in our series. And you can always go back to YouTube link, watch it again. The link is on Meetup. And thanks again for joining. Good night, everyone. I'm going to stop streaming now. I think that needs to happen first.
It's nice to be here. Stay dry, everybody. The storm's coming.
Yep. Well, it's a much needed rain, right?